All right, so today it's sixth week. Can you believe it? We're already over halfway through our quarter, and so it's just it's exciting here. All right, so what we're going to talk about today is floating point arithmetic. Okay. Did we cover this already? Why? Okay, so so for the first half of the course, this was a complaint that some students had in their feedback, but this is kind of the course design. The first half was mostly focused on R programming and learning all of those, the nitty gritty, all of that, and then the second half is going to be kind of our foray into computational statistics, and this is computational statistics kind of at a big picture level is about using the computer to answer difficult questions that are either statistically or related to statistics or probability. Okay, and so some of this will involve computational methods to find answers, okay, as opposed to analytic answers, right? So when you take calculus and you do algebra, you can do these things and you get, you can find the zeros of a function or the minimum or the maximum. And here we'll look at computational methods that allow us to find, the same kinds of answers, but without learning any actual math. I mean, of course there's math, but we're taking a computational approach. So to understand how some of these things work, we have to understand maybe some of the major differences between regular math and computer math, okay? And when I talk about computer math, what I'm talking about is floating point numbers. So we're accustomed in algebra, we are accustomed to dealing with real numbers, and when you're dealing with real numbers, you have rules that are ingrained to us, right? Like the order of addition doesn't matter, the order of multiplication doesn't matter, right? If you group things, you got your commutative property, and then your associative properties. What are these? No, these are like the things, right? Like A times the group B plus C is equal to A times B plus A times C, and things like that. And it doesn't matter whether you do B plus C first and then multiply by A, or if you do A times B first and then do A times C and then add those two together, right? Those are the things that we're accustomed to in all of our years of math and algebra, and we take these things for granted. When we're dealing with a computer, those rules no longer apply. Like these things that we've held sacred regarding the way we do mathematical operations no longer hold true, especially at these small decimal levels, okay? And in fact, the way the computer does things, it's very hard to kind of predict very well. And so today we'll talk about floating point precision and maybe just some of the pitfalls and warnings, and we just have to kind of keep this in mind as we do certain operations, okay? So this is implemented at a hardware level in your computer, okay? So, we all have, probably almost all of your computers use Intel chips, and pretty much all the main chips on the market will use this. And this is, we use the IEEE 754 standard, okay? And I think they recently had they have like the 1985 and then the 20-something, 2000, whatever version. This is kind of the standard. You can look this up on Wikipedia and learn about how these things are stored. And this is done at a hardware level, so whether you are dealing with R software or you're using Python or C, these numbers are stored in the computer the same way because it's done at a hardware level. It's not specific to your programming language. Okay, and as we know, in the computer, we store values using binary, right? So, we've got binary numbers. And if we want to express the number 5, we would write 101 because this is our ones place. This is 2 to the 0. This is the 2's place, 2 to the 1. And this here is the 4's place. And that's, 2 squared. So this corresponds to 2 squared plus 0 plus 2 to the 0, which is 4 plus 1. And that's the number 5. Right? Okay. And so this would be binary numbers. And if we have fractional binary numbers, we could write something like 101, and then we would put a dot here. And because this is now in binary, this would be called a binary point versus the decimal point. Okay, and then so what do you think the first spot after the binary point would represent? Not the tenths, but the halves, right? This would be the halves, and this would be the quarters, and this would be the eighths, right? So this would be the half, quarter, and eighth. Okay, and then so what would this number would now be 5 plus 1/2 plus 1/8, and so this would be 5 and 5/8, so 5.625. This is the binary equivalent of that. Okay. All right. Is that okay? We have a fractional binary. So this is, maybe we want to be able to store a number like this in our computer. Okay. Okay. And so as computer engineers were trying to figure out, all right, well, let's figure out how we should store numbers and stuff. They said, okay, well, we only have a finite amount of memory, right? You can have 16 gigabytes of RAM, but that's still only 16 gigabytes, right? And technically, there's an infinite number of values, and you can have, in any one number, could have an infinite number of trailing decimals, right? And so it's simply not feasible to store a single number with an infinite number of trailing decimals or trailing binary places in the computer. So the engineers said, okay, we are going to say each number will take up a certain amount of bits, right? And this is as precise of a number as we can express, and for most of the time that's fine, okay? And so, nobody complains that when they're on the calculator they only have 10 digits on the screen, right? But effectively, because we are using just a finite number of spaces to represent a potentially like the real numbers have infinite things, there's going to be problems. Okay, so for example, just so we have only a finite number. Something's funny with my pen here. We only have a finite number of digits to represent a value. So this is effectively the problem that we have, and I'll do it with a decimal number, right? Okay, so we'll go back to decimal, all right? And let's say your calculator only has, just for simplicity, say 6 digits on the screen here, okay? And so let's say you do the operation 10 divided by 3, okay? What would your calculator output? 3.33333, right? And this is with six places here, right? Okay, so this is our number. We got 6 digits here. Okay, and then let's say we take this number, 3.333, and I multiply it by 3. What am I going to get? I'm going to get 9.99999, right? Because in basically in floating point, or in basically in finite, I don't know how to write right now, in finite representation, 10 divided by 3 is equal to 3 and 3,330 whatever over 1 millionths, or wait, no, 100 thousandths. Sorry, thank you. Okay, so these two values are equal when we have finite representation. And so when you have a number like this stored in the computer, okay, the computer doesn't know, oh, I've got 3.33333. Is that 10/3, where there's actually an infinite number of 3's continuing on? Or is that 3 and 33,333 100,000ths? The computer has no idea. It actually doesn't care. It has no opinions on the matter. And in its mind, these two things are equal. And therefore, when you take this and you multiply it by 3, when we take 3.33333 and multiply by 3, we do not get the same, we do not get 10. Okay, and that's effectively the problem in a nutshell. Okay, and so these are just things you've got to keep in mind, that if I do some kind of change here, this is not going to work. I mean, if you have your laptop out, you can try this, and you can ask, is 0.1 plus 0.2, is that equal to 0.3, right? And if you put that on the computer, it's going to say false. It's going to say false, right? And you're like, what? My whole world is falling apart. Yeah. So let me make the screen larger. Okay, sorry. Different class. Okay, so we've got, right, if I do 0.1 plus 0.2, it looks like it's correct, right? But then let's say I store this as A, and I say, is A equal to 0.3? And it's gonna say false. Okay, right? Okay, so if we, how do I do this? All right, so if I do format A, is it like with 16? No, how do I get the number of decimal places? Format digits equals 16. Let's try this. I don't know what's going on. All right. I forgot the command. Let me we'll do a quick check here. So our number of digits. Options. Okay, so we'll do options digits equals 16. All right. Now maybe I need 22. Okay, so that's what A is, right? So 0.1. So if we look at what 0.1 is and we look at what 0.2 is, this is what it is. 0.1 plus 0.2. This gives me this, and if I type in 0.3, it gives you that. Okay, and so because the computer is not able to, when you ask it for the value 0.1, it's kind of like, because it's binary, it's kind of like a situation where you're asking it to represent 10/3, and it's not going to be exactly the value here, right? And so it represents, the way it stores 0.1 in its memory is 0.1000001, and the way 0.2 is stored in memory is stored like this, and when you add those two together, it comes out like this, which seems crazy to us, right? And then if we ask, well, what is 0.3? Well, this is the number that represents 0.3 in the computer's memory, and so so this is where we're running into problems here, okay? And this is why 0.1 plus 0.2, is that equal to 0.3? That's going to be false, okay? So to solve this, we can use all equal, which says, are these two things close enough to each other? And the answer is going to be yes, it's close enough to each other in what we consider machine error. Yes?
When we were doing the previous homework, we were using the logical judgment of an object equals to a number all the time. So how can we get the correct result with the previous homework?
Yeah, so this is an issue when you're dealing with floating point numbers. When you've got, like if you have an integer or something, if you don't have a decimal, then 4 is represented as 4. It's just when I do 4.1, does it come out something different from what we might anticipate, okay? So these are things you have to keep in mind, right? When you are dealing with a number with a decimal, it has to represent that decimal number as close as it can using kind of the binary space. We are accustomed to seeing things in decimal, and so we understand that when we try to divide by 3, we're going to get like a infinite trail of 3s, and we get that, and that's very natural to us. But the thing is we're not dealing with decimal system, we're dealing with a binary system, and so representing things that are in tenths for a binary system is actually very challenging, right? In the same way that representing things in thirds or 2/3 in the decimal system is challenging, representing things with tenths and hundredths is actually challenging in the binary system, except when they're nice and neat, like if I do 1.25, that's represented as 1.25, which makes sense because 0.25 is something that's perfect in the binary system, okay? So these things work out in the binary system, but when we are dealing with something like 0.2 in the binary system, oh, well, I guess that one's okay. But in other things, it doesn't. Other tenths do not work out so nicely. Okay, and so internally, it's basically trying to represent a number with a bunch of infinitely repeating things and it has to just truncate it because it says, you know what? We have an allocated number of bits in memory that we're going to use for a number. Okay? All right, so there's a lot of details that we've got to cover regarding this. So let me pull out my thing. Okay. Okay, so for illustration, okay, so in the computer, we use double precision floating point numbers, right? Okay, so we have double precision floating point. There's also single precision floating point, but that doesn't exist in R. It exists in other languages, but not in R, okay? And so a double precision floating point number uses 64 bits or 8 bytes to store a number. Okay, so we have 64 1 and 0 positions, okay? One of these numbers, the first is for the sign. We have 11 bits for the exponent. And then we have what we call 52 bits for the mantissa. Okay, and so I've got, and then regarding the sign, 0 for positive and 1 for negative. Okay, and so here we're going to deal with what we call a mini float, and this is going to be, we're going to only use 8 bits to represent our number just for illustrative purposes, but the idea is the same. We're going to have 1 bit for the sign, this time 3 bits for the exponent, and 4 bits for the mantissa. Okay, so we have a mini float for teaching. Okay, and this will be 8 bits, 1 sign, 3 exponent, and 4 for the mantissa. Okay. Huh? Mantissa. Yeah, that's the word. Okay. I don't know. That's what they call it. All right. I don't know. It's the thing that's not the exponent. Okay. I don't know what it means. All right. We just call it the. So if we have these 8 bits, this is the sign, this is the exponent, and this is the mantissa. All right. You can look it up and try to see what we have. Okay, so let's say we wanted to represent the number 5.75, okay? So 5.75 in binary would be 101, that's the 5, and then the 0.75 would be 1/2 and 1/4, right? So this would be 5.75 in binary, right? Oh, so well, this is just in binary representation. We haven't tried to put it in our mini float yet. Okay, so the way we're going to represent binary numbers in floating point is we turn everything into basically scientific notation. Okay, and so in scientific notation, basically, whatever the number is, you only have one leading number before your decimal point, or in this case, our binary point, okay? So we are going to put this in scientific. And we will have 1.0111 times, and now it's going to be 2 to the, we moved this over 2 spots, so it's 2 to the 2, or if we wanted to be pedantic about it, it would be 1.0111 times 2 to the 10, if we're going to be pedantic. But that's what we have, right? And we can kind of compute this out I'm just going to close our screen here. And so this effectively becomes 1 plus, not a half, but a quarter, 1 plus 1/4, plus 1/8 plus 1/16 times 2 squared, or times 4, right? And if we look at this, we have 1 plus 0.25 plus 1.125 plus 0.0625, and that turns out to be 1.4375. And if we multiply that by 4 times 4, we do indeed get 5.75. Okay, so it does work and everything. And so what we would do is we say, okay, this is the number we're going to represent, 1.0111. And in our thing, we're going to say, okay, because everything is in scientific, we can assume that the leading digit is always a 1, right? Because if you put something in scientific notation, you're only going to have a single number before the decimal or binary point, right? And because it's binary, it can only be a 1, right? If there was a 0 leading, then you would just move the binary point over somewhere, right? So we can, because it's always going to be in scientific notation, that leading number is always going to be assumed to be a 1, right? Okay, so now we're going to just do, okay, we're going to put 0, 1, 1, 1 into the mantissa. So here, so I'm going to put 0, 1, 1, 1. This part goes into the mantissa. And then this is a positive number, so our sign is 0, okay? We have to do something special to the exponent to put it in here, okay? So the exponent is not going to be, it's technically 2 to the 2 squared, or 2 to the 1, 0. So you would think we would put in 0, 1, 0 here for the exponent, but we have to do something special to the exponent first, okay? Okay. Okay, so far, okay? All right. Okay, so here, with our exponent, we want to be able to express both negative and positive numbers, right? Because sometimes we want to say, because we want the ability to express small numbers, we want to have the ability to have a negative exponent, right? So want to be able to express negative exponents as well, right? Okay, so here I've got, we have 3 bits for the exponent. Okay, so how many unique values can I represent using the exponent? Yeah, there is a sign bit, right? We have 1 sign bit, right? So if we look at it, we've got 1 for the sign, 3 for the exponent, and 4 for the mantissa. Okay, so this is the exponent, this is the mantissa, and this is the sign. Oh, I'm sorry. So with the exponent, yeah, the exponent itself doesn't have a sign bit. We have basically 8 numbers that we can represent, right? 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 110 and whoops. 110 and 111. Okay, so we have a total of 8 numbers, and so what we're going to do, and these correspond normally to the value 0, 1, 2, 3, 4, 5, 6, 7. What we want to do is we want to be able to express both positive and negative numbers, so we add what we call a bias. Okay, we bias these numbers. And so now 0, 0, 0 will map to the number -3. This will map to the negative number -2, -1. This represents 0. This represents 1, 2, 3, and 4. So with a biased scheme, this is called a biased scheme for binary numbers. Basically, we say, all right, these are the 8 unique values that we can represent here, and because we also want negative and positive numbers, we're going to use a bias of -3. Yes?
Is this related to like the maximum value in R? Because I believe that R has some kind of
Yes, yes, we I can talk about that, but maybe not right now. Okay. Okay, so this is what we're gonna do, and so earlier we said we have the number 1.0111 times 2 to the second, right? And so if we look at this, 2 is going to be represented by the pattern 101, or effectively a 5. There's a bias of 3 here. Okay, so we so the exponent 2 is represented with a 5, with a 101. Okay, so the value in floating point is going to be 0 for the positive, 101. This is a biased 2, and 0, 1, 1, 1 for the decimal component, or not the decimal, the binary, the fractional component here. Okay, so what is the bias that we're going to use? Okay, well, the bias is basically, well, we said 2 to the third is 8 numbers, so those are the how many unique values I can use. Okay, we want half of those to be positive, and then the other half to be negative and 0. So the bias is going to be basically 2 squared minus 1. So that's how we got -3. So the bias for an exponent with n bits is 2 to the n minus 1 minus 1. So in this case, we have 3 bits. So it's 2 to the 3 minus 1. 2 squared minus 1 is 4 minus 1, 3. Bias is 3. Okay. So if in the IEEE 754, in the floating point system that our computer uses, we have 11 bits for the exponent. What is the bias that we use? We have 11 bits for the exponent. Yeah, 2 to the 10, which is 1024 minus 1, so we have a bias of 1023. Okay, so whatever number you have, you add 1023 to that, and then you convert that into binary. Okay, so if you have an x2 to the 0, if that's what you have, then it's going to be 2 to the you're going to represent 1023 in binary and put that in there, and that allows you to have an exponent of up to 2 to the minus 1023. Okay, is this okay? Okay, we have a few special cases here we've got lots of special cases actually. If we're gonna run out of time. If all the exponent bits are a 1 and the mantissa is all zeros, then that is infinity. Yeah, so you have a positive and negative infinity. So this is when you're when R represents infinity and negative infinity in the computer's memory, it's basically this. This is positive infinity. And then if you have a 1 up here and all ones and all zeros, this is negative infinity. So this is how our computer, the computer actually doesn't have infinity. It just has a way to represent infinity. So when you ask the computer for infinity, this is what it's giving you, okay? And then so the computer also represents not a number, right? NaN is anything where you have all ones up here and then something other than all zeros. So if you have something other than all zeros, this is going to be not a number. All right, so whether you have, okay, so as far as our floating point numbers go, right, 111, this represents, because it's got a bias of 3, this is only 2 to the 5th or something. Wait, what was the last slide I had there? 2 to the 4th, okay. So going larger than that, 2 to the 4th, it basically gets to 2 to the 4th, which is 16. Anything bigger than that is going to be infinity in the mini float system, okay? In R, and yeah, we're running out of time. There's more to the floating point system, but you can represent probably 2 to the 1023, all right? 2 to the 1024 is going to be infinity, right? If I do 2 to the 1023 plus 2 to the 1023, this will say it's infinity. If I say 2 to the 1022 plus 2 to the... so this is not infinity, but then if I take this and if I add something to it, like 1022, then it becomes infinity. No, it just goes, we only have not a number. We don't have a negative not a number.